The cosmos was once a perfect and profound darkness. This is not a metaphor, but a chapter in our universe's history, a mysterious era astronomers call the Dark Ages. It was the long silence between the fading afterglow of the Big Bang and the brilliant dawn of the very first stars. For hundreds of millions of years, the universe was a shadowy sea of simple gas, holding its breath. What could possibly happen in an epoch with no light to see it? By the end of this exploration, you will know 30 of the most compelling theories that attempt to solve this ultimate cosmic cold case. We will venture from the solid ground of established physics to the wild shores of speculation, uncovering how this silent era forged the galaxies and set the stage for everything that followed. Could the seeds of our own existence have been planted in that ancient dark? To understand the mystery, we must first understand the stage. The leading scientific framework for the universe's story is known as the Lambda CDM model, and it paints a very specific, almost serene picture of the Dark Ages. This is our baseline, the established timeline against which all other theories are measured. According to this model, the Dark Ages began around 380,000 years after the Big Bang, a moment called recombination. At that instant, the universe cooled enough for protons and electrons to finally combine and form the first atoms, almost all of them simple hydrogen and helium. With that union, a brilliant fog lifted. For the first time, light could travel freely across space. That light is what we detect today as the cosmic microwave background, a snapshot of the infant cosmos. And then silence fell. From that point on, for the next 100 to 200 million years, the universe entered its long, quiet chapter. There were no stars, no galaxies, no quasars. The cosmos was a vast, expanding sea of nearly uniform neutral hydrogen and helium gas, kept in the dark by two dominant but invisible forces. The first is dark matter, an unseen gravitational scaffold that was already pulling matter into the faintest of clumps. The second is dark energy, a mysterious pressure that would later drive the universe's accelerating expansion. In this era, these dark components worked in the background while the ordinary gas simply drifted, cooling and waiting. It was a universe of profound simplicity and profound stillness, a blank canvas of pure potential. Every galaxy, every star, every planet that would ever exist was contained within that dark, diffuse cloud. The Standard Model tells us this was not an empty void, but a pregnant darkness filled with the raw ingredients of everything to come. It is the foundation of our cosmic story, the quiet prologue written in hydrogen and shadow. But what if the darkness wasn't quite so uniform or so quiet, but the Standard Model's quiet prologue contains a hidden, essential actor? While the sea of hydrogen gas drifted in darkness, another, more mysterious component was already at work, weaving the first threads of cosmic structure. This is the role of dark matter halos. Unlike the ordinary atoms we are made of, dark matter does not interact with light or the electromagnetic force at all. It is, for all intents and purposes, invisible, but it does feel gravity, and in the expanding universe of the Dark Ages, gravity was the only sculptor that mattered. Tiny, random quantum fluctuations from the universe's first moments, imprinted on the cosmic microwave background, gave dark matter a slight head start. Regions that were ever so slightly denser had a tiny bit more gravitational pull. Over millions of years, this pull acted like a cosmic magnet for more dark matter. Particle by unseen particle, these regions grew, collapsing into vast spherical clouds. Astronomers call these structures dark matter halos. They became the universe's hidden architecture, an invisible skeleton stretching across the darkness. Without the light and pressure from stars to push it away, the neutral hydrogen and helium gas, what scientists call baryonic matter, simply followed the gravitational blueprint laid down by these halos. Imagine a vast, invisible bowl forming in the fabric of space. ordinary gas like water naturally flows down into the gravitational well at its center. The dark matter halo provided the deep potential well, the trap that could finally gather and hold the raw fuel for star formation. As time flowed on in the Dark Ages, these halos grew through mergers, and by pulling in more material, their gravitational grasp strengthening. They nested inside one another, with smaller halos orbiting within larger ones, creating a complex, unseen web. This was the crucial preparatory work. The first protogalaxies were not built from starlight outward, but from this dark matter scaffolding inward. The long silence of the era was not an empty wait, it was a period of immense, invisible construction. Every brilliant galaxy we see today, including our own Milky Way, was once just a whisper of extra density in the dark matter field, a seed of gravity patiently growing in the dark. So the universe was not a featureless void, it was a canvas where an unseen hand was already sketching the outlines of everything to come. But what could possibly ignite the first spark within these gathering clouds of gas? Yet within those gathering clouds of gas, a silent chemical revolution was taking place. To ignite the first stars, the universe needed more than just gravity, it needed a way to shed heat. This is where a simple molecule becomes the hero of our story, molecular hydrogen. In the primordial soup, almost all hydrogen existed as single, isolated atoms. But when two hydrogen atoms bond together, they form molecular hydrogen, or H2. This molecule is special because it can vibrate and rotate, and when it does, it emits a tiny amount of infrared radiation. That emission acts like a cosmic radiator, allowing a cloud of gas to cool down. Think of a hot piece of metal glowing red. It is radiating away its heat. Molecular hydrogen let the primordial gas do the same thing on a cosmic scale. As the gas cooled, it lost the internal pressure that was fighting against gravity's pull. This allowed the gas to condense further, growing denser and hotter at its core, inching ever closer to the temperatures needed for nuclear fusion. But forming this crucial coolant was not easy. In the pristine environment of the early Dark Ages, there were no dust grains to act as meeting platforms for atoms. Instead, the primary catalyst was the humble free electron. A hydrogen atom could temporarily grab onto a passing electron, forming a negative ion. This gave the atom a sort of sticky shield, allowing another hydrogen atom to latch on and form the precious H2 molecule before the electron drifted away. It was a fragile, inefficient process. This is what astronomers call the molecular hydrogen cooling bottleneck. The formation of H2 was so slow and delicate that it put a severe brake on star formation. Gravity was eager to collapse the gas, but without efficient cooling, the gas would just heat up and bounce back like a spring. This bottleneck meant the first stars could not form quickly. It forced the gas to accumulate slowly over millions of years within the largest and deepest dark matter halos, where gravity's grip was strongest. The first stars were not born in a rapid burst of creation, but in a long, slow cosmic simmer. The entire fate of the luminous universe hinged on the difficult birth of this simple, two-atom molecule in the dark. The silent chemistry of molecular hydrogen set the stage, but the first stars to ignite would become agents of chaos. Theory 4 reveals a self-regulating mechanism that emerged with the dawn of light itself, known as the Lyman-Werner feedback. The very first stars were not like our sun. They were colossal behemoths, hundreds of times more massive and ferociously hot. Their furious nuclear furnaces blasted the surrounding darkness with intense ultraviolet radiation. But not all ultraviolet light is the same. These massive stars produced a specific type of photon with just the right amount of energy, falling into what astronomers call the Lyman-Werner band. And these particular photons had a devastating effect on the cosmic coolant molecular hydrogen. When a Lyman-Werner photon strikes an H2 molecule, it does not simply heat it up, it breaks the chemical bond apart, dissociating the molecule back into two separate, lonely hydrogen atoms. This process is like a cosmic off switch for star formation. Imagine a single brilliant campfire igniting in a vast, dark forest. Its light is so harsh and specific that it prevents any dry kindling nearby from being able to catch a spark. That is what happened in the early cosmos. A massive star would blaze to life, and its Lyman-Werner radiation would create a growing bubble of destruction around it, a zone where the crucial molecular hydrogen could not survive. Within this bubble, the raw gas could no longer cool efficiently. The very process that allowed that first star to form was now actively preventing new stars from forming in its immediate neighborhood. This created a powerful negative feedback loop. Star formation would begin to grind to a halt in the regions closest to the massive stars, potentially delaying the birth of the next generation. It forced cosmic structure to become more complex and spread out, as new stars had to ignite farther away, in gas that had not yet been sterilized by this harsh ultraviolet light. This feedback mechanism did not just influence local star formation, it had profound implications for the entire universe's transition out of the Dark Ages. By regulating the pace at which new stars could ignite, it directly influenced the timeline of reionization, the great cosmic dawn that would eventually flood the universe with light. The first stars were not just creators of light, they were also destroyers of potential, governing the rhythm of creation from their very first brilliant, disruptive breaths. These monstrous first stars are known to astronomers as population 3 stars. They were the universe's original pioneers, forged from nothing but the pristine hydrogen and helium of the Big Bang. Without any heavier elements to act as impurities or efficient coolants, the physics of their birth was radically different. Gravity could gather far more material before the heat from compression finally triggered fusion, resulting in behemoths of unimaginable scale. Current theories suggest a typical population 3 star could have been anywhere from 50 to 1,000 times the mass of our Sun. Picture a single star that outshines an entire modern galaxy, a searing pinpoint of ultraviolet fury burning at over 100,000 degrees. Their lives were as intense as they were brief. A star like our Sun has a lifespan of 10 billion years, but these primordial giants burned through their nuclear fuel in a cosmic blink, perhaps only 2 or 3 million years. Their spectacular deaths were as formative as their births. The most massive might have collapsed directly into black holes without a supernova, vanishing from the visible universe. Others would have detonated in cataclysmic explosions known as pair instability supernova, events so powerful they would leave no remnant behind, blasting their entire being back into space. But it was in these violent deaths that the Dark Ages truly met their end. For the first time, the supernova forged and scattered heavier elements like carbon, oxygen, and iron across the cosmos, poisoning the pristine gas for future generations. This chemical enrichment meant stars that formed later, population 2 and our own population 1 Sun, could form from richer, cooler material, leading to smaller, longer-lived stars. More crucially, the intense radiation from these living stars and the shockwaves from their deaths began to rip electrons from the neutral hydrogen atoms around them, creating growing bubbles of ionized plasma. Population 3 stars did not just pierce the darkness, they assaulted it. Each one was a cosmic revolution, ending the silent era not with a whisper, but with a thunderous series of brilliant, transformative explosions that changed the fundamental rules of the universe. The violent end of those first stars did more than seed the cosmos with new elements. It began to fundamentally change the universe's very state of matter. This brings us to the pivotal theory of cosmic reionization, the great dawn that finally ended the Dark Ages. Reionization is the process where the intense ultraviolet light from the first stars and galaxies, and potentially other exotic sources, blasted through the cosmic fog. This radiation carried so much energy that it could rip the single electron right off a neutral hydrogen atom, splitting it back into a free proton and a free electron, creating a soup of charged particles called a plasma. In essence, the universe was being reionized, returned to a hot, conductive state similar to its first few 100,000 years, but now for an entirely different reason. This was not an instant flip of a light switch. Instead, imagine a vast, dark continent at night. First, a single, brilliant campfire ignites, then another and another. Slowly, the fires grow in number and their circles of light begin to overlap, pushing back the shadows in patches. Over hundreds of millions of years, these bubbles of ionized plasma grew and merged until the entire cosmic landscape was once again flooded with light, completing the transition from a neutral to an ionized universe. The timeline of this process is one of cosmology's greatest detective stories. We know it was largely complete by the time the universe was about 1 billion years old, but when did it start and how long did it truly take? Was it a slow, steady brightening or a rapid, tumultuous series of bursts? Even more pressing is the mystery of the primary light sources. Were the first massive population 3 stars alone powerful enough to drive this cosmic transformation? Or did the feeding supermassive black holes at the hearts of early galaxies, known as quasars, contribute a significant, perhaps dominant, blast of ionizing radiation? Current observations suggest that early, faint galaxies likely did the bulk of the work, but the contribution from quasars remains a hotly debated piece of the puzzle. Unraveling the story of reionization is not just about understanding the end of an era. It is about identifying the true architects of the luminous cosmos we inherited. The story of reionization is written in the fading light of those first stars, but to truly witness the dark ages themselves, we need a different kind of eye. This brings us to a theory that is not about what ended the darkness, but how we might finally observe it directly. It is called the 21-centimeter forest theory, and it offers a potential window into the universe's silent chapter. The key lies with the humble hydrogen atom, the sole occupant of that era. Even in its neutral, quiet state, a hydrogen atom is not completely inert. The proton and electron that form it each act like tiny magnets, and they can be aligned in 2 ways, either with their magnetic poles pointing in the same direction or in opposite directions. Every so often, the electron will spontaneously flip its spin. This quantum flip releases a very specific, faint whisper of radio energy with a wavelength of exactly 21 centimeters. During the Dark Ages, the entire cosmos was filled with a fog of neutral hydrogen, each atom capable of emitting this faint signal. As the universe expanded, that signal stretched or redshifted to much longer wavelengths. By the time it reaches us today, the primordial 21-centimeter whisper from the heart of the Dark Ages has been stretched into radio waves meters or even tens of meters long. But here is the ingenious part: this signal would not be a uniform hum. It would be a forest. Imagine you are trying to listen to a distant radio station, but between you and the transmitter are countless other objects like trees that absorb specific frequencies. In the cosmic version, the first bright sources that eventually formed, like quasars or early galaxies, would have acted as backlights shining through the vast fog of neutral hydrogen. The hydrogen gas at different distances, and therefore from different times during the Dark Ages, would absorb the 21-centimeter radiation at specific, redshifted frequencies. The resulting spectrum would look like a dense forest of absorption lines, each line a fingerprint from a specific slice of the ancient cosmos. Studying this forest would give us an unprecedented 3-dimensional map of the universe during its darkest era. The depth of each absorption line would tell us the density of the gas at that point in time and space. More astonishingly, the temperature of the gas affects the strength of the signal. By reading this cosmic barcode, we could chart the heating and cooling of the universe before any stars were born, potentially seeing the subtle influence of the very first dark matter annihilations or the infall of gas into those early dark matter halos. Capturing this signal is the holy grail for several monumental projects, most notably the Square Kilometre Array, or SKA. This next-generation radio telescope, being built across South Africa and Australia, is designed with the sensitivity to potentially tune into this primordial radio whisper from over 13 billion years ago. If successful, it would not just be a new observation, it would be a time machine, allowing us to watch the cosmic canvas in the moments just before the first brushstrokes of light were applied. But what if the dark matter halos themselves were not made of unknown particles, but of ancient, invisible objects born in the fire of the Big Bang? This brings us to one of the most provocative theories in cosmology, the idea that dark matter could be composed of primordial black holes. These are not the stellar black holes formed from collapsing stars, but hypothetical monsters forged in the extreme density and turbulence of the universe's first second. Imagine microscopic regions where the newborn cosmos was so intensely packed that gravity overcame the explosive force of the Big Bang itself, causing pockets of space to pinch off directly into black holes. These objects could range in mass from something smaller than an asteroid to many times the mass of our Sun, all formed before a single atom even existed. If they are real and abundant, they could solve two cosmic mysteries at once, explaining the nature of dark matter and providing ready-made seeds for cosmic structure. During the Dark Ages, these primordial black holes would have been the ultimate dark matter candidates, invisible yet possessing immense gravitational pull. They would have begun gathering the neutral hydrogen gas around them far earlier and more efficiently than the smooth dark matter particles of the Standard Model. A swarm of these ancient black holes could have jump-started the formation of the first stars and proto-galaxies, acting as gravitational anchors in the void. The first luminous objects in the universe might not have formed in the centers of diffuse dark matter halos, but instead as glowing accretion disks around these invisible primordial hearts. The hunt for evidence is on. Scientists look for their subtle signatures in the modern cosmos. One method is gravitational microlensing. If a primordial black hole passes in front of a distant star, its gravity will bend and magnify the star's light, causing a characteristic temporary brightening. Surveys scanning millions of stars have found a handful of these unexplained events, but not enough to confirm the theory. Another clue comes from the ripples in spacetime we call gravitational waves. The mergers of black holes detected by observatories like LIGO could include pairs of primordial black holes that have been dancing around each other since the dawn of time. The masses and spins of some detected black holes do not perfectly match predictions from stellar evolution, leaving a tantalizing window open for a primordial origin. If this theory is correct, the Dark Ages were not sculpted by a smooth, mysterious particle field, but by a hidden population of fossilized cosmic traps, their silent gravity writing the first draft of everything to come. While primordial black holes offer a dramatic alternative, another theory suggests the dark matter scaffold itself might have been built from lighter, swifter material. This is the theory of warm dark matter. The standard lambda CDM model relies on cold dark matter, particles that move sluggishly compared to the speed of light, allowing them to clump together easily from the very beginning, forming that intricate hierarchy of halos from the largest scales down to the very smallest. But what if the dark matter particle was different, something lighter and faster? Candidates like the hypothetical sterile neutrino, a heavier, right-handed cousin to the ordinary neutrinos that stream through us, could fit this description. Warm dark matter particles would have zipped through the early universe with significant thermal motion, a kind of subatomic jitter that prevents them from settling down into the tiniest gravitational wells. This motion acts like a cosmic smoothing iron, washing out the smallest density fluctuations. The result is a universe where the very first dark matter structures to form are not countless microscopic clumps but larger, warmer puddles. The implications for galaxy formation are profound and directly address a modern puzzle known as the missing satellites problem. Our Milky Way is surrounded by a swarm of small dwarf galaxies, but simulations based on cold dark matter predict there should be many, many more of these tiny satellite galaxies than we actually observe. Warm dark matter offers an elegant solution. It suppresses the formation of those very smallest dark matter halos from the outset. There simply would not be as many gravitational traps to host a tiny dwarf galaxy, bringing theory closer to what we see today. For the Dark Ages, this changes the entire ignition sequence for the first stars. In a warm dark matter cosmos, the first star-forming halos would be rarer and more isolated, but they could also potentially form earlier. Without a cascade of tiny halos forming first, the available gas might be funneled more efficiently into the fewer, larger wells that do emerge. The first proto-galaxies might be brighter beacons in a darker, emptier void, with vast stretches of pristine hydrogen lying undisturbed between them. The cosmic dawn might have been illuminated not by a dense, twinkling field of early sparks, but by a smaller number of brilliant, isolated lighthouses, their radiation carving out immense bubbles in the neutral fog. This single change to the fundamental nature of the unseen majority of matter rewrites the opening chapters of structure, suggesting the darkness was not finely detailed, but painted in broader, lonelier strokes. The nature of dark energy is arguably the greatest mystery in modern cosmology. We see its effect today, a mysterious force causing the expansion of the universe to accelerate over the last several billion years. But the standard model assumes it was essentially dormant, a negligible whisper during the universe's first chapters. Theory 10 challenges that assumption with a radical idea. What if dark energy was not a constant, but a dynamic actor that also played a crucial role in the Dark Ages? This concept is known as early dark energy. Imagine the force driving cosmic expansion today was far more potent in the universe's infancy. An early phase of intense dark energy would have acted like a powerful cosmic accelerator, causing space to stretch at a much faster rate during its first few 100 million years. This is not a minor tweak to the timeline. It is a fundamental rewrite of the environment in which the first structures had to form. Gravity is a patient sculptor, but it needs time to work. When two particles of matter feel a mutual gravitational pull, they begin to drift toward each other. But if the space between them is expanding too quickly, that drift can be overcome, like two swimmers trying to reach each other in a current that keeps pulling them apart. An early surge of dark energy would have made the cosmic fabric more slippery, suppressing the growth of those initial density fluctuations. The gentle tug of dark matter halos on the surrounding hydrogen gas would have faced stiffer competition. This could have delayed the collapse of the first gas clouds, pushing back the ignition of the very first stars and the subsequent dawn of reionization. The long cosmic silence of the Dark Ages might have been extended by this invisible, repulsive pressure. But why consider such a dramatic revision? The clues come from subtle tensions in our modern observations. Precise measurements of the universe's current expansion rate, known as the Hubble constant, derived from nearby galaxies, seem to disagree slightly with predictions based on the ancient cosmic microwave background. One compelling proposal to resolve this Hubble tension is to invoke an early dark energy phase. This early burst would have altered how sound waves propagated in the primordial plasma, changing the cosmic microwave background's fingerprint in a way that, when projected forward, aligns perfectly with the faster expansion rate we see today. If this theory holds, it means the Dark Ages were not unfolding in a calmly expanding arena, but in one being actively stretched and smoothed by a powerful, unseen repulsion. The large-scale cosmic web we see today, the vast filaments and voids, would bear the subtle imprint of that ancient struggle between the relentless pull of gravity and this fleeting primordial push. The first stars did not just fight against the darkness, they may have had to ignite against a cosmic tide. gravity is not the only force that could have written on the blank slate of the early cosmos. Some theories suggest the universe's infancy was marked by deep structural flaws, cracks in the very fabric of reality that could have guided its growth. These are cosmic strings, hypothetical one-dimensional defects thought to have formed during the universe's rapid cooling in its first moments. Picture the universe undergoing a profound phase transition, like water freezing into ice. As it cooled and settled into a new, more stable state, imperfections could have been locked in, not as bubbles or cracks, but as unimaginably thin, vibrating filaments of pure energy stretching across the entire cosmos. Each one would be a flaw in space-time itself, narrower than a proton but denser than a mountain range, with a gravitational pull so intense it would warp everything around it. During the Dark Ages, these cosmic strings would have been the ultimate cosmic fishing lines. Their immense gravity would have acted as a direct trap, pulling the diffuse neutral hydrogen gas toward them from great distances. Matter would have flowed along these invisible threads, condensing into dense, linear rivers of gas within the dark. This presents a startling possibility. The very first structures to light up might not have been isolated, spherical halos, but brilliant, aligned beads on a string. The collapse of gas and the ignition of the first population 3 stars could have been strung out along these primordial filaments, creating the earliest linear constellations in the universe. These starry necklaces would have been ephemeral, as the intense radiation from the newborn stars would have quickly heated and disrupted the delicate gas filaments that birthed them. Yet their brief existence could have left a lasting imprint. If cosmic strings were abundant, they might have provided a ready-made blueprint, accelerating the initial collapse of matter and offering a faster, more directed path out of the darkness than gravity alone. While no definitive evidence for cosmic strings exists, scientists look for their ghostly signatures in the cosmic microwave background, searching for telltale step-like discontinuities in temperature or in the subtle distortions of light from distant galaxies. Finding one would be more than a discovery. It would be a direct snapshot of the universe's fiery infancy, a fossilized crack from the moment of creation that may have drawn the first lines of light in the dark. The universe's first light shows were not its only spectacular events. While the first stars blazed and died, they may have also left behind another, invisible legacy woven into the fabric of space itself: cosmic magnetic fields. Today, magnetic fields thread through galaxies, sculpting gas clouds and guiding cosmic rays, but their origin is a profound mystery. They were not present in the smooth, hot soup of the Big Bang, so they must have been born sometime after. A leading theory points to the chaotic end of the Dark Ages as the cosmic forge where magnetism was first hammered into existence. One compelling idea is known as the Biermann battery effect. Picture the shockwave from one of those first catastrophic supernova racing out into the pristine gas. In such a violent, turbulent environment, differences in temperature and pressure can create subtle electric currents. According to a fundamental principle of electromagnetism, where you have swirling electric currents, you generate a magnetic field. The Biermann battery effect suggests that the first supernova explosions acted as cosmic dynamos, generating incredibly faint seed fields, trillions of times weaker than a common refrigerator magnet. These fields were not born strong, but they were born everywhere, imprinted like a faint watermark on the expanding bubbles of enriched material. Another potential birthplace was within the first collapsing protogalaxies themselves. As vast rivers of gas swirled and sheared under gravity's pull, the same basic principles could have converted that chaotic motion into a weak, large-scale magnetic imprint. Once these seed fields existed, the universe had billions of years to amplify them. The process is akin to a cosmic dynamo. Imagine taking a weak magnetic field and stretching it, twisting it, and folding it through the turbulent motions of ionized gas within a spinning galaxy. Over countless rotations, this repeated stretching and folding can amplify a whisper of magnetism into the powerful fields we observe today, shaping how stars form and how galaxies evolve. The weak seed planted in the violence of the cosmic dawn ultimately grew to become one of the universe's great invisible architects. The faint magnetic seeds of the cosmos may have been born in violence, but another, more pervasive form of darkness could have been quietly generating its own heat. This brings us to a theory that connects the smallest particles to the largest scales, the possibility of supersymmetric dark matter annihilation. Our journey through particle physics leads us to a leading candidate for dark matter, the weakly interacting massive particle, or WIMP. According to a theoretical framework called supersymmetry, every known particle in the Standard Model has a heavier, shadowy twin partner. The lightest of these supersymmetric particles is stable, neutral, and would barely interact with ordinary matter, making it a perfect WIMP candidate. If these particles are real, they would have been forged in the fiery first moments of the Big Bang and now permeate every corner of space, including the dark matter halos of the early universe. The key to their cosmic influence lies in a unique property. When two WIMP meet, they can annihilate each other, converting their entire mass into a burst of pure energy. This energy emerges as high-energy photons, electrons, positrons, and other exotic particles. Now, imagine the dense cores of the first dark matter halos during the Dark Ages. They were not smooth clouds, but likely had incredibly dense, cuspy centers where these hypothetical WIMP would have been packed together in staggering numbers. In these dense knots, the rate of annihilation would have been significant. Each annihilation event was a tiny, silent fireworks display, releasing energy directly into the surrounding sea of neutral hydrogen gas. This process would not have produced visible starlight, but it would have provided a steady, diffuse source of heat. The high-energy particles and photons from the annihilations would have collided with the hydrogen atoms, gently warming the gas. This subtle heating could have had two profound effects. First, warmer gas is harder to collapse. The gentle warmth from dark matter annihilation might have acted as a cosmic space heater, slightly delaying the gravitational collapse of gas clouds and pushing back the timeline for the formation of the very first stars. Second, some of the high-energy photons could have had enough energy to knock electrons off hydrogen atoms, causing a faint background level of ionization. This means that even before the first star flickered to life, the universe might not have been perfectly dark and neutral. Vast regions could have been faintly glowing with the soft X-ray haze of annihilating dark matter, and the gas could have been slightly pre-warmed and pre-ionized. The cosmic dawn, when it finally arrived, would have ignited in an environment that was already subtly prepared by the invisible decay of its own hidden scaffolding. While this background glow would be incredibly difficult to detect today, its potential influence is written into the fine details of the 21-centimeter forest we hope to observe. The depth and shape of those absorption lines could reveal whether the primordial gas was colder or warmer than the Standard Model predicts, offering indirect evidence for the whispers of annihilating WIMP from the depths of time. While WIMP whisper through annihilation, another ghostly particle might have broadcast its decay across the cosmos. This is the theory of sterile neutrino decay, a scenario where a shadowy cousin of the familiar neutrino could have gently warmed the entire universe from within. Ordinary neutrinos are among the most abundant particles in existence, streaming through you by the trillions every second, yet they interact so feebly they are nearly impossible to detect. The sterile neutrino is a hypothetical heavyweight relative, a particle that does not even feel the weak nuclear force, making it utterly dark and even more elusive. If sterile neutrinos exist with a specific mass in the kiloelectronvolt range, they would have been produced in vast numbers in the hot early universe and would now form a major component of dark matter. Their crucial property is instability. Over astronomical timescales, a sterile neutrino could spontaneously decay into an ordinary, lighter neutrino and a burst of high-energy radiation, an X-ray photon. Now picture the Dark Ages once more, that vast, quiet sea of hydrogen. It is not empty, it is suffused with this invisible fog of sterile neutrinos, each one a tiny, ticking clock. Their decay would not be a localized event like a supernova, but a universal phenomenon, a soft, uniform drizzle of X-ray photons raining down on every hydrogen atom in existence. This gentle rain would have had a profound effect. It would have heated the gas. The cosmic microwave background radiation provided a baseline chill, but this decay radiation would have added energy, raising the temperature of the neutral hydrogen above that primordial cold. This subtle, all-pervasive heating could rewrite the signature of the Dark Ages. The strength of the 21-centimeter signal we hope to detect is exquisitely sensitive to the temperature difference between the hydrogen gas and the cosmic microwave background. If sterile neutrino decay warmed the gas uniformly, it would reduce that critical temperature contrast, potentially making the cosmic whisper from that era even fainter, or imprinting a specific, recognizable pattern across the entire sky. Detecting or ruling out this effect is one of the key goals for next-generation radio telescopes. A confirmed signal would do more than reveal the thermal state of the ancient cosmos. It would identify the dark matter itself as a particle that lived, died, and left its warming mark on the universe long before the first stars were born. But the sterile neutrino is not the only ghost in the cosmic machine. Another, even more ethereal candidate whispers from the realm of quantum theory, offering a dark matter composed not of discrete particles, but of a pervasive cosmic field. This is the theory of axion dark matter. Axions are hypothetical particles born out of a solution to a deep puzzle in particle physics concerning the strong nuclear force. They are predicted to be incredibly light, billions or even trillions of times lighter than an electron, but they would have been produced in staggering numbers in the early universe. Because of their minuscule mass, axions behave less like billiard balls and more like waves on cosmic scales, governed by the strange rules of quantum mechanics. Their wavelength can be astronomical, meaning a single axion's wave could stretch across an entire galaxy. This wave-like nature leads to a breathtaking possibility. Under the cold, quiet conditions of the Dark Ages, these countless axion waves could have synchronized and coalesced not into stars, but into something even more exotic, a Bose-Einstein condensate. In a laboratory, scientists can cool certain atoms to near absolute zero, at which point they lose their individual identities and merge into a single, coherent quantum state, a superatom that behaves as one entity. On a cosmic scale, the vast, cold expanse of the early universe could have acted as the ultimate laboratory, allowing axions to undergo this same transition. The result would be colossal, diffuse clouds of coherent quantum matter, structures astronomers call axion stars or axion miniclusters. These would not shine with any light, but their gravitational influence would be profound and peculiar. Imagine the dark matter halos of the early universe not as smooth, featureless spheres, but as containing strange, swirling cores of this quantum condensate. These axion stars would create unique, oscillating gravitational potentials, subtle wells and peaks in the fabric of space that pulsed with a rhythm dictated by quantum physics. This pulsating scaffold could have directly guided the collapse of ordinary hydrogen gas. The first pockets of baryonic matter might have been drawn not just to the center of a halo, but to the specific, rippling nodes within these axion condensates. It presents a vision where the first structures were orchestrated by the gentle, wave-like interference patterns of a quantum field that filled the cosmos. The formation of the very first stars might have been a quantum process amplified to a cosmic scale, their birthplaces selected by the silent, rhythmic dance of an invisible substance that is less a particle and more a whisper woven through space itself. The quantum whisper of axions suggests a gentle scaffold, but the early universe was also capable of forging far more violent seeds. The colossal black holes that anchor galaxies today, some weighing billions of times our sun's mass, present a profound timing problem. They appear fully grown in the universe's youth, leaving astronomers to ask, how did they get so big, so fast? The answer may lie in the dark ages themselves, with the theory of pre-galactic black hole seeds. These would be the primordial kernels from which the modern monsters grew, and their formation likely followed one of two dramatic paths. The first path begins with the death of the universe's pioneer stars. Recall those behemoth population 3 stars, hundreds of times the sun's mass. When one of these giants reached the end of its brief, furious life, it might not have exploded at all. Instead, if it was massive enough, its core could have collapsed directly under its own weight, bypassing a supernova to forge a black hole of perhaps 50 to 100 solar masses. This is the heavy seed scenario, a stellar corpse of remarkable heft. These black holes would then lurk at the centers of the first protogalaxies, beginning a slow feast on the surrounding gas. But there is a catch. Even a 100 solar mass seed would need to devour matter at an almost impossible rate for billions of years to reach the sizes we see in the early cosmos. The math is tight, pushing against the limits of time itself. This tension leads to the second, more extreme theory, direct collapse black holes. Imagine one of those early dark matter halos gathering a vast reservoir of pristine hydrogen gas. In the standard story, the gas fragments into many stars, but under very specific conditions, this fragmentation might be prevented. If the gas cloud is kept warm and free of the cooling effects of molecular hydrogen, perhaps by the harsh ultraviolet light from a nearby massive star, it could avoid splitting apart. Instead, the entire giant cloud, weighing tens of thousands of solar masses, could begin to collapse in on itself as a single, monolithic entity. With no nuclear fusion to halt the inward plunge, this direct collapse would be a catastrophe of gravity alone. The cloud would simply vanish behind an event horizon, giving birth to a black hole seed thousands of times more massive than its stellar counterpart from the very first moment. This is a seed with a head start, a ready-made anchor point for a future supermassive black hole. But these seeds were not just passive sinks. As they formed and began to feed, they would have become brilliant beacons in their own right. Infalling gas swirling at near light speed in a glowing accretion disk would have released torrents of radiation, potentially outshining entire infant galaxies. A direct collapse black hole seed actively feeding could have been one of the most luminous objects in the early universe, a dazzling point of X-rays and ultraviolet light punching through the neutral fog. These seeds, whether heavy or direct collapse, would have done more than just grow. They would have shaped their surroundings from the beginning. Their fierce radiation could have heated and ionized local bubbles of gas, regulating star formation around them and contributing to the early stages of cosmic reionization. They became the gravitational hearts around which the first true galaxies assembled, their immense pull helping to bind stars and gas together. The supermassive black holes we see today are not late arrivals. They are likely primordial fixtures, their seeds sown in the unique physics of the Dark Ages, where the line between a collapsing gas cloud and a cosmic abyss was perilously thin. The violent birth of those first black hole seeds reveals the extreme physics at play. But what if the first stars never ignited through fusion at all? A startling alternative suggests the earliest beacons in the cosmos were fueled by something far stranger, the annihilation of dark matter itself. These hypothetical objects are called dark stars. In this radical scenario, a collapsing cloud of hydrogen gas would have encountered an incredibly dense knot of dark matter at its center, perhaps a remnant from the earliest halos. If that dark matter consisted of particles like WIMP, their mutual annihilation would have provided a powerful and steady source of energy. As the gas cloud shrank, the dark matter annihilation rate would have soared, generating an immense outward pressure. This pressure could have perfectly balanced the inward crush of gravity, halting the collapse before the core ever became hot and dense enough to spark nuclear fusion. The result would be a star, but one fundamentally alien to anything we know. A dark star would be a vast, puffy, and relatively cool globe, glowing with the soft, warm light of annihilating dark matter, rather than the fierce ultraviolet blaze of hydrogen fusion. Freed from the need to maintain crushing internal pressures for fusion, these stars could have grown to truly monstrous proportions. Theoretical models suggest they could have ballooned to millions of times the mass of our Sun and stretched to the size of our entire solar system. Their luminosity, while diffuse, could have rivaled that of a small galaxy, shining for millions of years on the steady decay of their dark matter fuel. This presents a profound shift in the narrative of the cosmic dawn. Instead of a sky punctuated by brief, brilliant pinpoints of fusion-powered giants, the early universe might have been illuminated by a few colossal, long-lived orbs of soft light. These dark stars would have been enduring lighthouses, bathing vast regions in a gentle, persistent glow. Their prolonged radiation would have slowly and steadily heated and ionized the surrounding hydrogen, potentially smoothing out the process of reionization. The end of the Dark Ages might not have been a dramatic series of explosive bursts, but a gradual brightening, as if a dimmer switch were being slowly turned up across the cosmos. The ultimate fate of a dark star is as fascinating as its life. Once its central reservoir of dark matter was finally exhausted, the balancing act would fail. Gravity would take over, and the star would undergo a final, catastrophic collapse. This collapse could trigger conventional fusion at last, leading to a supernova of unimaginable scale, or it might plunge directly into a massive black hole, providing yet another pathway to those crucial early seeds. While purely theoretical and intensely debated, the dark star concept challenges our most basic assumptions about what a star can be, suggesting the first light might have been a ghostly echo of the universe's own hidden architecture. The ultimate source of all cosmic structure lies in a moment of unimaginable violence before time itself had meaning. To understand the patterns written into the Dark Ages, we must rewind far beyond the first stars, back to a fleeting epoch known as cosmic inflation. In the first trillionth of a second after the Big Bang, the universe is thought to have undergone a period of exponential, faster-than-light expansion, inflating from a subatomic speck to a volume far larger than our observable cosmos. This violent stretching did more than create space, it also imprinted it with a fundamental texture. According to quantum mechanics, empty space is not truly empty. It seethes with fleeting virtual particles that wink in and out of existence. During inflation, these microscopic quantum fluctuations in the energy field driving the expansion were stretched to astronomical proportions. A random, subatomic shimmer of more here and less there in that primordial field became, as space ballooned, a continent-scale variation in density. When inflation ended, these frozen ripples in space-time were the only game in town, the sole blueprint for all future structure. They became the primordial seeds of gravity. Slightly denser regions meant slightly stronger gravitational pulls, and over the next 13.8 billion years, those tiny differences dictated everything: the distribution of galaxies, the vast cosmic web of filaments and voids, and the very first dark matter halos of the Dark Ages. The map of the modern universe was drawn in quantum ink during that first infinitesimal moment. We can still read that map today, not by looking at galaxies, but by studying the afterglow of the Big Bang itself, the cosmic microwave background. This ancient light, released 380,000 years after the Big Bang, carries a snapshot of those density variations at the end of the Dark Ages prelude. The subtle hot and cold spots we see in the CMB are not random. They follow a precise statistical pattern, a fingerprint of inflation's quantum origins. This pattern tells a powerful story. It reveals that the initial fluctuations were nearly, but not perfectly, scale invariant. This means the variations in density were roughly the same strength on all scales, from the size of a galaxy cluster down to the size of a single star-forming cloud. This single property, baked into the cosmos during inflation, dictated the hierarchical nature of structure formation. It ensured that small dark matter halos formed first, merging to build larger ones in a bottom-up assembly that would eventually light the first stars. The precise statistical character of those CMB fluctuations, their strength and distribution, set the initial conditions for the entire Dark Ages saga. They determined how quickly gravity could overcome the expansion of space, where the first overdense regions would emerge, and even the typical mass of those first star-forming clouds. Every event we have explored, from the slow gathering of molecular hydrogen to the ignition of population 3 stars, was playing out on a stage whose dimensions and contours were set in that first, fleeting instant. The long silence of the Dark Ages was not a blank slate. It was the unfolding of a script written in quantum code during the universe's first breath. Those quantum ripples from inflation set the initial conditions, but the infant universe was far from silent. In the fiery plasma before the Dark Ages, a cosmic symphony was playing out, and its final, frozen note became a permanent ruler etched into the cosmos. This is the theory of baryon acoustic oscillations. For the first 380,000 years, the universe was a searing, opaque soup of light and matter. In that dense fluid, gravity tried to pull the clumps of matter together, but it faced a powerful opposing force, radiation pressure from the intense light. This push and pull created massive sound waves or pressure waves that rippled outward from every initial overdensity at nearly half the speed of light. Think of dropping a stone into a still pond. The ripples expand in a perfect circle. In the primordial plasma, each dense region was like that stone, sending out a spherical wave of compressed matter and radiation. Then, at the moment of recombination, the music stopped abruptly. When atoms formed and the fog cleared, the photons raced away, leaving the matter behind, frozen in place. The result was a cosmic fossil. Each of those ripples left a distinct signature, a subtle preference for matter to be clustered at a specific distance from the center of those ancient waves. That distance, about 500 million light-years across today, is known as the baryon acoustic oscillation scale, and it acts as a standard ruler imprinted across the entire universe. We can see this ruler clearly in the large-scale structure of the modern cosmos, in the distribution of millions of galaxies. But the theory proposes this same signature, this same frozen wave, should also be imprinted in the distribution of neutral hydrogen during the Dark Ages itself. Back then, before stars stirred everything up, the pattern would have been even cleaner, a pristine fossil of that primordial sound. The hydrogen gas, pulled by gravity into the dark matter halos, would have preferentially gathered along those ancient spherical shells. This means the map of the Dark Ages, the one we hope to read through the 21-centimeter forest, should contain this faint, repeating pattern of clustering at a very specific scale. Detecting it would be a monumental achievement. It would provide a direct, powerful test of our entire cosmological model. By measuring the apparent size of this standard ruler at different cosmic times, we could trace how the universe has expanded throughout its history with incredible precision. We could measure the expansion rate during the Dark Ages itself, a period currently shrouded in mystery. It would act as a cross-check, anchoring our understanding of dark energy and the geometry of space. Future 21-centimeter surveys, like the Square Kilometer Array, are designed with this exact goal in mind. Finding the baryon acoustic oscillation signal in the ancient hydrogen would be like discovering the original tuning fork used to set the pitch for the cosmic symphony, a perfect note preserved in the long silence before the first stars began to sing. The smooth dawn of reionization is a compelling story, but the truth was likely far messier. Theory 20 introduces the concept of a lumpy or inhomogeneous reionization. This is the idea that the universe did not transition from dark to light in a uniform, global fade, but in a chaotic, patchwork fashion, more like the breaking of a storm across a landscape. Instead of a single rising tide of ionizing photons, imagine countless local downpours. Each cluster of early stars and galaxies acted as its own powerful ionizing source, blasting out ultraviolet radiation that carved a growing bubble of ionized plasma into the surrounding neutral hydrogen fog. These bubbles were not neat spheres but irregular, amoeba-like structures, their shapes dictated by the density of the surrounding gas and the ferocity of their central sources. As more luminous objects ignited, their individual bubbles expanded and began to touch, merging into ever larger ionized regions. Yet between these growing bubbles of light, immense tracts of pristine, neutral hydrogen persisted, dark continents in an increasingly luminous sea. Astronomers often describe this topology as cosmic Swiss cheese, where the ionized bubbles are the holes and the neutral hydrogen is the cheese. For hundreds of millions of years, the universe was this bizarre, fragmented place, a mosaic of brilliant plasma and profound shadow. The growth rate and ultimate shape of these bubbles is now a primary target for observation. By studying the patterns in the most distant light we can see, from quasars and early galaxies, scientists look for the statistical signature of this patchwork. Did the bubbles grow quickly once they formed, or did they expand slowly, fighting against the relentless recombination of atoms in dense gas? Were they driven primarily by numerous small galaxies, or did a few brilliant quasars punch out disproportionately large cavities? The answers lie encoded in the subtle way these ancient bubbles imprint themselves on the light that passed through them. The journey of a photon from the first billion years is a story of running a gauntlet, being absorbed and re-emitted countless times by neutral hydrogen atoms at the edges of these bubbles. That journey leaves a specific fingerprint on the spectrum of the light that finally reaches us. Decoding that fingerprint is how we map the topography of the end of darkness, revealing not a simple sunrise, but a turbulent, fragmented dawn where light fought its way out, one bubble at a time. The fragmented dawn of reionization was lit by ultraviolet starlight, but another, more penetrating radiation may have been at work. Theory 21 points to the influence of cosmic dawn X-ray binaries. In the chaotic nurseries of the first protogalaxies, not all massive stars died alone. Some were born in binary pairs, and when one exploded, it could leave behind a dense remnant, a neutron star or a stellar mass black hole. If this remnant remained gravitationally bound to its companion, a deadly dance would begin. The intense gravity of the remnant would begin to strip gas from the outer layers of the living star, pulling that material into a swirling, superheated accretion disk before it vanished over the event horizon. This process releases a torrent of high-energy radiation, not in the ultraviolet but in the form of powerful X-rays. An X-ray binary is a lighthouse of a different, more insidious color. While ultraviolet photons are easily absorbed by the outer layers of a neutral hydrogen cloud, X-rays are penetrators. They can travel deep into the heart of a vast, dark gas cloud before being absorbed, depositing their energy throughout the entire volume, not just on the surface. This creates a diffuse, internal heating effect. Imagine the difference between warming your hands by a campfire and being inside an oven. The heat is everywhere at once. For the gas clouds that were destined to form the second and third generations of stars, this pervasive heating could have been a decisive factor. To form a star, a cloud must collapse, and to collapse, it must cool. X-ray heating works directly against this, providing a source of energy that keeps the gas puffed up and turbulent. This would have particularly suppressed the formation of low-mass stars. Smaller stars form from smaller, denser knots within a cloud, knots that are more easily disrupted and evaporated by this internal warmth. The result would be a shift in what astronomers call the initial mass function, the statistical distribution of stellar sizes at birth. In an X-ray heated environment, the cosmic scales would have been tipped. Fewer red dwarfs and sun-like stars might have formed, while the formation of massive stars could have been relatively enhanced as they require larger, more resilient reservoirs of gas to collapse. If X-ray binaries were common in the early universe, they would have acted as invisible regulators in the stellar nurseries, their piercing radiation subtly sculpting the populations of stars that would go on to build the first galaxies. The legacy of those first binary deaths might be written in the ancient stellar fossils we find in our galactic halo today, a record of a time when the darkness was not just banished by light, but gently cooked from within by a faint, pervasive glow. The heat of X-ray binaries paints a picture of a warm, ionizing dawn, but the process might have unfolded in a far chillier fashion. Theory 22 proposes a radical alternative, a cold reionization. This model challenges the standard fiery narrative, suggesting the end of the Dark Ages was not a blazing inferno, but a more prolonged, subtle glow. The key lies in the nature of the first light sources themselves. What if the first stars were not the monstrous, searing population three giants we have imagined? Some simulations allow for a different initial mass function, where the very first stellar generation included a significant number of smaller, cooler stars. These stars would have been less massive than our Sun, burning at lower temperatures and emitting a much softer spectrum of ultraviolet light. While they would still produce ionizing photons, their output would be gentler, less aggressive. Furthermore, the structure of the earliest galaxies could have played a crucial role. The escape fraction is a critical term in cosmology, referring to the percentage of ionizing photons that actually escape a galaxy's gaseous cocoon to flood the intergalactic medium. In modern galaxies, this fraction is very low as dense gas clouds trap and absorb the radiation internally. But the first proto-galaxies were likely tiny, fragile things with far less gas and dust to obstruct the light. If these infant systems had extremely high escape fractions, perhaps approaching 80 or 90%, then even a population of relatively faint, cool stars could have efficiently ionized their surroundings. Their photons would not be wasted heating local gas, but would instead stream freely into the cosmic voids. The result would be a reionization process that was more widespread but also much cooler. Instead of fierce ultraviolet blasts creating hot, pressurized bubbles, a cold reionization would be like a slow, pervasive fog lifting. The intergalactic gas would be ionized, but its temperature would remain remarkably low, as it was not being violently heated by intense radiation. This has profound implications for the cosmic story we are trying to decode. A colder intergalactic medium would have behaved differently, affecting how subsequent generations of galaxies formed and clustered. Most tantalizingly, it would leave a distinct signature in the 21-centimeter forest. The strength of that ancient hydrogen signal depends on the temperature difference between the gas and the cosmic microwave background. In a cold reionization scenario, that difference would be smaller, potentially making the absorption lines we seek even fainter and more difficult to detect, but also imprinting a unique pattern across the sky. A cold dawn suggests a universe that woke up gently, its transition marked not by brilliant, localized fireworks, but by a slow, quiet brightening from countless modest embers, a cosmic awakening where the lights came up slowly and the room stayed surprisingly cool. Our cosmic detective story faces a profound and humbling limitation. We can only observe a single universe and from one fixed point within it. This introduces a critical concept known as cosmic variance, a statistical fog that clouds our view of the Dark Ages. The principle is simple yet profound. The patch of sky we can see from our vantage point, no matter how powerful our telescopes, might not be perfectly representative of the universe as a whole. Think of it like trying to understand the global climate by studying the weather in your own backyard for a single year. Your data is real and valuable, but it might not capture the full range of possibilities from desert droughts to monsoon seasons. During the Dark Ages and the subsequent dawn of reionization, this effect was especially potent. Cosmic structure was just beginning to form, and the first luminous sources were rare and clustered. Imagine the early universe as a vast, dark ocean where the first islands of light are just beginning to emerge. From our single, fixed location billions of years later, we are looking back along one specific, narrow line of sight into that ancient sea. What if, by pure chance, our particular line of sight passes through an unusually dense region, a supercluster in its infancy? Our observations would suggest the first galaxies formed earlier and more densely than they did on average across the cosmos. Conversely, if our view looks out through a primordial void, we might conclude the cosmic dawn was later and more sparse than it truly was. This variance is not an error in our instruments, it is a fundamental limit imposed by our place in space and time. It directly affects our ability to draw definitive, global conclusions about the most pivotal processes. When we measure the timeline of reionization, for instance, we are essentially taking a core sample from one location in the cosmic ice sheet. That sample tells us a true story, but is it the only story? Could reionization have completed 200 million years earlier in one direction and 200 million years later in another? Cosmic variance forces us to be cautious, reminding us that our grand theories about the universe's youth are based on a single, possibly quirky, snapshot. It injects a necessary humility into our search, a recognition that the ultimate truth of the Dark Ages might be richer, stranger, and more varied than our one precious view can ever fully reveal. Cosmic variance reminds us our view is limited, but what if our fundamental physics is also incomplete? This brings us to a theory that challenges the very scaffolding of our cosmic story, the theory of modified Newtonian dynamics, or MOND. For decades, the mysterious gravitational pull we attribute to dark matter has been the cornerstone of cosmology, the unseen hand that shaped the first halos. MOND proposes a radically different solution. Perhaps the pull is not from missing matter, but from a subtle flaw in our understanding of gravity itself. The theory was born from a stubborn observation: the rotation curves of galaxies. Stars and gas at the outer edges of spiral galaxies orbit far too quickly for the gravitational pull of the visible mass alone. Instead of inventing an invisible halo of dark matter, MOND suggests that Newton's laws of gravity, and by extension Einstein's, require a tiny modification under conditions of extremely weak acceleration. In the deep outskirts of a galaxy where gravity's tug is incredibly faint, the force might stop falling off with the square of the distance and instead follow a different, gentler decline. This single tweak can perfectly explain the observed rotation of galaxies without a single particle of dark matter. The implications for the Dark Ages are nothing short of revolutionary. Our entire narrative of that era is built upon dark matter halos acting as gravitational seeds, patiently gathering hydrogen gas for hundreds of millions of years. Take that scaffold away and the cosmic construction site looks utterly different. Without those dense, invisible wells of gravity, how would structure even begin to form? In a MOND-governed universe, the initial quantum fluctuations from inflation would still exist, but the force amplifying them would behave differently on the largest, most diffuse scales. The growth of overdensities might be slower, or it might proceed in a more top-down fashion, with large-scale sheets and filaments forming before fragmenting into smaller pieces. The first objects to condense could be vast, wispy clouds of gas, not the compact, dense cores we envision within dark matter halos. The formation of the very first stars becomes a monumental puzzle. Without a deep gravitational well to trap and compress gas, what mechanism could possibly trigger that initial catastrophic collapse? Perhaps turbulence and sheer mass alone in these immense primordial clouds could reach a critical threshold. Or maybe the first luminous objects in a MOND universe were not isolated stars at all, but enormous, diffuse proto-galaxies that ignited whole regions of star formation at once. The timeline of the cosmic dawn would be completely rewritten, potentially delayed or occurring in a sudden, coordinated flash. Furthermore, the process of reionization would have a different geography, shaped by these larger, flatter structures rather than by bubbles growing around isolated halo centers. Wileman successfully explains many galactic-scale phenomena. It struggles with other evidence, like the gravitational lensing of massive galaxy clusters, which seems to require dense, unseen mass. Yet its existence as a compelling alternative force is a profound question. Are we interpreting the silence of the Dark Ages through the wrong fundamental lens? The long wait for the first light might not have been a gathering in dark matter wells, but a slow, universe-wide shift in the very rules of attraction. A cosmic change so subtle it rewrote gravity itself before a single star could shine. Even the radical revision of gravity cannot erase a persistent cosmic anomaly. For all their power, our theories of dark matter and modified gravity still struggle to perfectly predict the precise arrangement of galaxies we see in the sky, the subtle statistical clustering that emerged from the primordial dark. One audacious proposal suggests the answer lies not in changing the rules of our universe, but in doubling its contents. This is the theory of a mirror or shadow sector, a realm of highly speculative physics where every particle we know has a hidden twin in a parallel cosmic domain. In this vision, the universe contains not just one set of particles, protons, electrons, and neutrinos, but two complete, independent copies. These shadow particles would interact with each other through their own forces, a mirror of our own strong and electroweak interactions, but they would be utterly blind to our photons, our atoms, our light. The only bridge between our world and the shadow world would be the universal contractor, gravity. Both sectors would feel the same gravitational pull, woven from the combined mass of both visible and shadow matter. This means that during the Dark Ages, while our familiar hydrogen gas drifted in the darkness, an entire unseen cosmos of shadow particles could have been undergoing its own parallel evolution. Shadow dark matter halos would have formed, shadow molecular hydrogen might have cooled, and perhaps even shadow stars ignited, all in a ghostly duplication of the processes happening in our own sector. These structures would be completely invisible to every telescope ever built, for they emit no light, no radio waves, no signal we could ever detect directly. Yet their gravitational influence would be inescapable. Imagine two transparent sheets of glass, each with intricate patterns etched upon them. Held apart, you see only one pattern at a time. But stack them together, and the combined image becomes more complex, the lines appearing thicker, the intersections creating unexpected nodes of density. This is how a shadow sector could have sculpted the cosmos we see. The gravitational wells that gathered our first hydrogen clouds would have been deepened and shaped not just by our dark matter, but by the hidden mass of entire shadow galaxies forming in the same location. This could explain why some large-scale structures seem more pronounced, or why certain voids appear emptier than our standard models predict. The distribution of the first luminous galaxies might bear the subtle, amplified fingerprint of two separate cosmic blueprints laid perfectly atop one another. The long silence of our dark ages might have been, for a shadow universe, a period of brilliant and busy creation. Its light forever locked away in a dimension of reality we can only feel through the faintest of gravitational tugs. The most profound theories of quantum gravity suggest our cosmic origin story may be incomplete. Within frameworks like loop quantum cosmology, the Big Bang might not have been a true beginning but a transition. This theory proposes a universe that undergoes endless cycles of expansion and contraction, a cosmic heartbeat across eons. In this view, our expanding cosmos emerged from a big bounce, rebounding from an immensely dense, hot state that was the final moment of a previous universe's collapse. If this is true, then something extraordinary might have survived that transition. Not information, not energy as we know it, but potential remnants of spacetime itself pushed to its absolute limit. These are hypothetical objects known as Planck stars. A Planck star is not a star in any conventional sense. It represents the ultimate quantum gravitational object, a state of matter so compressed that it reaches the Planck density, where the very fabric of spacetime is expected to foam and churn with quantum uncertainty. According to the bounce theory, such an object would not form a true singularity, but would reach this maximum possible density and then rebound, exploding outward. The staggering implication is that some ultra-dense cores from the pre-bounce universe could have been catapulted into our new cosmic dawn. These would be fossils from a time before time, relics of an earlier cosmic phase. During the Dark Ages, such an object would be utterly invisible, a knot of quantum spacetime with the mass of an entire galaxy compressed into a volume smaller than an atom. Yet its gravitational pull would be immense and point like a perfect, infinitely deep well in the smooth dark matter field. If even one such Planck star remnant drifted through a primordial cloud of hydrogen, it would act as a gravitational trigger of unparalleled efficiency. The gas would not need to slowly accumulate over millions of years within a diffused dark matter halo. Instead, it would be sucked violently toward this microscopic, supermassive anchor. The first collapse around a Planck star seed would be swift and catastrophic, potentially forging the very first supermassive black holes or igniting the first colossal stars in a fraction of the usual time. These remnants would be vanishingly rare, but their impact would be disproportionate. A single Planck star could seed an entire future galaxy cluster, explaining how supermassive black holes appeared so early in the cosmic record. Their existence would mean the Dark Ages were not a blank slate, but a canvas upon which the ghostly fingerprints of a previous universe were already pressed, guiding the hand of creation from the very first moment of our own. The universe's first second left behind more than just a fading afterglow of light. It also generated a ghostly sea of nearly massless particles that still washes through everything today, the cosmic neutrino background. Created just 1 second after the Big Bang, these neutrinos have been streaming through space for over 13 billion years, a relic as fundamental as the cosmic microwave background but far more elusive. For the hydrogen gas adrift in the Dark Ages, this neutrino sea was a constant, whispering presence. While neutrinos famously pass through entire planets without a single interaction, their sheer unimaginable abundance means that statistically, some would have gently brushed against the primordial atoms. These interactions are not the stuff of dramatic collisions. Instead, they could occur through two subtle channels. The first is simple gravitational scattering. Every particle with mass, even the tiniest neutrino, warps the fabric of spacetime around it. As a fast-moving neutrino passed near a hydrogen atom, its minuscule gravitational tug could have imparted a tiny amount of kinetic energy, like a cosmic pebble skipping across a still pond and creating the faintest of ripples. The second, even rarer possibility is a direct weak force scattering, where a neutrino actually strikes a proton or electron within the atom. Either way, the result was a transfer of energy, a microscopic heating event. Individually, each interaction was vanishingly small, a whisper lost in the void, but collectively, across hundreds of millions of years and quintillions of neutrinos permeating every cubic centimeter of space, this could have added up to a diffuse, universal warmth. This neutrino heating would have been a background hum, a gentle and pervasive energy source acting on the gas everywhere at once. It would not have sparked ionization or driven dramatic collapse, but it would have subtly raised the baseline temperature of the cosmic hydrogen above the chilling effect of the expanding universe. This slight warming could have had a delicate influence on the timeline of star formation. Cooler gas collapses more easily. If the neutrino background kept the gas even a fraction of a degree warmer, it might have slightly delayed the moment when the deepest gravitational wells could finally overcome thermal pressure and trigger collapse. It is a reminder that the Dark Ages were not a perfectly passive environment. Even in the profound stillness, the universe was alive with the faintest of energies, a sea of ancient ghosts from the first second of time, gently touching the future with imperceptible hands. The faint warmth of the cosmic neutrino sea was a gentle whisper, but the universe was also capable of a scream. This brings us to a theory of a far more violent dawn, the possibility that the first light to truly tear apart the Dark Ages did not come from stars at all, but from the voracious mouths of the universe's first monsters. This is the theory of first light from quasars. Quasars are the brilliant, blazing cores of distant galaxies, powered by supermassive black holes feeding on staggering amounts of gas. As matter spirals into the abyss at near light speed, it forms a searingly hot accretion disk that can outshine an entire galaxy of stars. The standard story places these titans later in the cosmic timeline, after the first galaxies had already assembled. But a radical revision asks, what if they came first? What if the seeds of those supermassive black holes, born from direct collapse or the remnants of population 3 stars, began to feast almost immediately? If conditions were just right, a seed of only a few thousand solar masses could have begun a runaway feast, pulling in the surrounding pristine hydrogen at a ferocious, unsustainable rate. This rapid accretion would have turned it into a miniature quasar, a pinpoint of unimaginable ferocity in the otherwise silent dark. The radiation from such an object would be of a different character entirely from starlight. A quasar does not just glow, it blasts. Its emission is beamed and concentrated, a focused torrent of high-energy X-rays and ultraviolet photons that can punch through gas clouds that would absorb the softer light of stars. This changes the physics of reionization dramatically. While the first stars carved out relatively small, hot bubbles in the neutral fog, an early quasar would be a blowtorch. Its intense, beamed radiation could have tunneled through vast distances, ionizing and heating enormous, elongated cones of space. It would not create a spherical bubble, but a long, narrow corridor of plasma, like a searchlight sweeping through a dense cosmic mist. The heating effect would also be extreme, raising the temperature of the intergalactic gas in these regions to millions of degrees, effectively sterilizing it and preventing local star formation for eons. This leads to a profound debate. Could these early quasars have been the primary drivers, the great disruptors that ended the Dark Ages? Their efficiency at ionizing distant gas is undeniable, but their rarity is a problem. Were there enough of them early enough to matter on a cosmic scale? Or were they simply dazzling outliers, brilliant but rare fireworks in a dawn primarily illuminated by the countless, humble first stars? The answer may be written in the pattern of the cosmic microwave background's polarization, and in the temperature of the most ancient intergalactic gas we can measure. If quasars played a leading role, we would expect to see evidence of this intense, patchy heating and highly structured ionization from the very beginning. The end of darkness might not have been a gradual brightening from countless campfires, but a series of sudden, searing flashes, as if the cosmos were being lit by lightning strikes long before the sunrise. The journey from darkness to light might have been a story of false starts and second chances. Some of the most sophisticated computer simulations of the early universe paint a startling picture, one where the cosmos did not simply wake up once but twice. This is the theory of a double reionization. In this scenario, the first violent generation of population 3 stars acted like a cosmic flashbang. Their sudden, brilliant ignition would have flooded their immediate surroundings with a torrent of ionizing ultraviolet radiation, carving out the first large bubbles in the neutral hydrogen fog. But these pioneer stars were not built to last. Their lives were spectacularly short, ending in cataclysmic supernova after only a few million years. When they died, the primary source of ionizing photons in their region would have vanished almost overnight. the intense radiation pressure that was holding the ionized bubbles open would have ceased. In the dense, cooling gas left behind, free protons and electrons could have begun to find each other once more, recombining back into neutral hydrogen atoms. The bubbles of light would have begun to shrink, and the darkness would have crept back in, at least partially. For a time, the universe could have experienced a strange twilight, a partial return to neutrality in vast regions that had briefly known the blaze of the first stars. This would not have been a full reset to the pristine dark ages, as the gas was now enriched with heavy elements from those first supernova, but it would have been a significant reversal. Then the second act begins. From the ashes of that first failed dawn, a new and more stable population of stars begins to form. These are the smaller, longer-lived stars of population 2, forged from gas that now contains traces of carbon, oxygen, and silicon. These elements act as powerful coolants, allowing gas to fragment into smaller, more stable clumps. This generation of stars is less massive, less luminous individually, but far more numerous and enduring. They burn for billions of years, not millions. Alongside them, the first true dwarf galaxies begin to coalesce, providing a sustained, distributed source of ionizing radiation. This second wave of light would have been less flashy but infinitely more patient and relentless. Its photons would have pushed back the neutral hydrogen once more, but this time the sources did not blink out. The ionization fronts would have advanced steadily, merging and growing until they finally overlapped completely, achieving the permanent global reionization we infer today. A double reionization solves several nagging puzzles. It could explain why some observations of the most distant quasars show hints of surprisingly neutral gas at later times than expected, as if some patches of the universe were slower to clear. It also provides a natural explanation for how the intense radiation from the first stars could have escaped their birth clouds to begin the process, only for that process to stall and then restart under new management. The cosmic dawn, then, may not have been a single sunrise over a still landscape, but a dawn punctuated by a deep, mysterious lull, a cosmic breath held between two very different kinds of light. But this entire cosmic detective story, from quantum ripples to the final dawn of light, rests on a foundation of staggering precision. The physical constants that govern our universe, the strength of gravity, the mass of the electron, the exact energy levels in a hydrogen atom, all seem exquisitely fine-tuned. If any one of them were even slightly different, stars would not burn, molecules would not bond, and life as we know it would be impossible. This leads to a final, mind-bending theory that sits at the edge of science and philosophy, the theory of the multiverse and anthropic selection. What if our universe, with its specific 13.8 billion-year history and its particular 100 million-year dark ages, is not the only one? The concept of a multiverse arises naturally from several cutting-edge theories like eternal inflation. In this view, our Big Bang was not a unique event, but one bubble in an infinite, frothing sea of spacetime. Each bubble universe could have spontaneously inflated with its own random set of physical laws and constants. In an infinite ensemble of universes, every possible configuration would exist somewhere. Most of these universes would be stillborn, dark, or chaotic, their constants incompatible with the formation of any complex structure at all. But by pure statistical chance, a tiny fraction would have the precise, razor's edge conditions needed for atoms, stars, planets, and eventually, observers to arise. We, of course, find ourselves in one of those rare, habitable bubbles. This is the essence of the anthropic principle, a logical filter on our observations. We should not be surprised to see a universe finely tuned for life, because in a cosmos not tuned for life, there would be no one here to be surprised. Apply this lens to the Dark Ages. Was that long, quiet incubation period also a necessary part of the recipe? If the first stars had ignited too quickly, perhaps merging into monstrous black holes before galaxies could properly form. If reionization had been too slow, the cosmic web might have remained a diffuse, unproductive fog. The specific timeline, the delicate balance between the gathering power of dark matter and the cooling efficiency of molecular hydrogen, every bottleneck and feedback loop we have explored might represent a narrow path through a labyrinth of cosmic possibilities. Only on that path could a universe produce galaxies rich with heavy elements, solar systems with stable orbits, and planets with billions of years of chemical evolution. The profound silence of the Dark Ages, then, may not be a random historical detail. It could be a signature, a required chapter in the only kind of cosmic story that ever gets told, because it is the only kind that leads to creatures capable of looking back and wondering about the dark. This perspective does not answer the physical how, but it reframes the ultimate why. Our search for the first light is also a search for our own cosmic address, a way to understand not just how our universe began, but why this one of all possible universes became our home. From the solid ground of the Lambda CDM model to the wild shores of cosmic strings and dark stars, we have journeyed through a breathtaking landscape of ideas. This incredible diversity of thought reveals a profound truth. The Dark Ages were not an empty, silent chapter in our cosmic story. They were a dynamic laboratory for the most extreme physics, a cosmic workshop where the fundamental rules of reality were tested and the first seeds of everything were sown. For every established pillar, like the patient gathering of dark matter halos or the great dawn of reionization, there exists a radical alternative, from a universe gently warmed by sterile neutrinos to one illuminated by the ghostly glow of annihilating dark matter. This is not a sign of confusion, but of a science alive with possibility, pushing at the very edges of what we can know. And now, for the first time in human history, we are building the tools to move from speculation to observation. We are no longer limited to theoretical models and computer simulations. A new generation of cosmic observatories is coming online, designed to listen to the whispers of that ancient dark. The colossal square-kilometer array radio telescope will soon scan the skies, its millions of antennas tuned to detect the faint 21-centimeter signal from primordial hydrogen, aiming to map the cosmic web in its infancy. In space, the James Webb Space Telescope peers deeper into the infrared than ever before, hunting for the very first galaxies and the fingerprints of those first monstrous stars. These campaigns are not just missions, they are time machines. They will test our boldest theories, ruling out some and elevating others, transforming our picture of the universe's youth from a collection of intriguing ideas into a detailed, observable history. So the next time you look up at the night sky, at the glittering tapestry of stars and the faint smear of distant galaxies, remember this: every point of light you see was born from that long, profound darkness. The atoms in your body were forged in stars that themselves could only ignite because of the patient, invisible work of an era without light. We are the children of that dark age, living in the luminous aftermath of a silent revolution. The story of our cosmic dawn is still being written, and with every new observation we add another line. Which of these 30 theories captures your imagination the most? Is it the quantum whisper of actions, the brilliant flash of a first quasar, or the haunting possibility of a universe before our own? Let us know in the comments below, and if you want to join us for more deep dives into the greatest mysteries of space, be sure to subscribe. The universe's story is far from over, and the next chapter promises to be its most revealing.